Okay, so the idea behind this is that up to now we've been dealing with, and you don't need to draw this, but up to now we've basically been dealing with objects that are on a flat surface, right? And the vertical forces are balanced, and the horizontal ones, if they're balanced, stop or at constant velocity, and if they're not balanced, then it's accelerating. When you go onto an inclined plane, well, now you're sort of adding another dimension, so to speak, in reality, right? So what actually, if this is a frictionless plane, there's no friction or very little friction on here, what's going to happen to the object, the box on the ramp? It's going to slide down the ramp, right? I mean, everybody knows that, right? How come? Because of gravity, right? But isn't gravity straight down? So how come it goes that way, if gravity's straight down? Well, think back about the components that we've learned about, right? Gravity's straight down, but a component of that gravity is in fact, oops, right there. That's gravity right there. There's a component that actually sends it down the ramp. And the steeper the ramp, well, the greater that component is, right? If you imagine that the ramp was 90 degrees, well, the component of gravity is 100%. It's all down, right? And as that ramp sort of decreases, that's an arrow there, as that ramp decreases, right, then this thing here eventually gets down to like this, right? And that component of gravity is minuscule. It's hard to see. Let's deal with sort of an in-between one, though. We're going to label some things. Okay, so this one right here, which I will put in red, is in fact the weight force. Label that in. Gravity. That's gravity, pulling it down. And of course that's equal to mg. And this one here, now I label the components Fd and Fn. And the Fn is a little bit of a lie, a little bit of a gloss over. I'll try to fill in some background there. Okay? The normal force is really, like if it's sitting flat, the normal force is up, right? Okay? So that's, technically the normal force is that one. But there's a component of gravity that provides that normal force. And so on the box, I'm going to call this one here the normal force. Technically, it's, some books like to call it F perpendicular because it's perpendicular to the plane. I just find that Fn just sort of is, even though it's glossing over a little bit, I think it sort of makes things simple a little bit later down the road. Kind of thing. So those are the components, Fd and Fn. Now you might say, okay, well, but before we had like x and y components. How come we don't call them x and y? Some books actually do that. Some books will call down the plane x and up, they'll call that y. I find that a little bit confusing. Okay, I like to use Fd and Fn because it's sort of specific to this situation. All right. Okay, so you might, like I said, if you take physics somewhere else, post-secondary, you might see them labeled a little bit differently, but it's the same idea. Okay, let's talk about this angle right here, the angle of the ramp. Is there anywhere else in the diagram that you would see an angle that is equivalent, the same value? We'll play hot and cold here, Jake. Tell me when I'm getting warm. Right here? There? Oh, right there.
On the other side of the line.
The angle of diffraction.
Not that line, but that one. If you drew a line. If you could say it.
Right there? Come over here, Peggy. Yeah, come on up. It'll be fun. Oh, it's like The Price is Right. She's running up there.
If you draw it, I don't know how to draw on this thing. Like this one right there.
Where?
That one.
Oh.
If you drew a line, it'd be the same.
Oh, okay. Yeah, the Z, the interior opposite angles,
This one.
whatever thingy. I like to
And
think
that
of it
one.
as Z, right?
This one and that one.
I guess, but that has nothing to do with what we're going to do.
Well, then, just saying.
But you're right. I guess you're right. I just never thought of that.
You asked.
I did. Actually, the one I was hoping that you were going to say is this one right here.
I'll
And if I had that little interactive one, I could show it to you. I will show it to you later. But does that make sense to you that those two would be the same? You're in the minority, Brandy. If you think about this being straight up and down, right, and this angle here being 90 degrees, right, well then what's this one here going to be? It's going to be like this, right? It's going to be like that, isn't it? 90 degrees. And as you go down, right, as the whole thing rotates, here, let me see if I can do this. Let me see if I can do this. Oh, is that going to work? No, it's not. If you think about it going down to 0, if I get this right down to 0, then the normal force is equal to that, right? As I ramp up, that sort of spreads apart. Okay? I'll show it to you visually in a bit. That's important. This angle here, of course, is 90 degrees. This FD right here that I'm going to draw in black, this FD right here, quite often is also drawn right there. Because remember in the free body diagram, we want to draw it sort of from the block. But this one here is equivalent to that one there. I drew it a little longer than I should. Okay, because the FD is actually the force that what? Sends it down the plane. That's the accelerating force. That's the component of gravity that sends it down the plane. Okay, just to make sure I've covered it. So, when an object sits on an inclined plane, like the one we just saw, gravity acts to pull it down the plane, Fg. And gravity also acts to push it against the plane, perpendicular to the plane. Those are the two components of gravity in that situation. The one that's pulling down the plane, and the one that's sort of pulling it against the plane. Now, if there was friction, let's say it's down a rough surface. If there was friction, where would there be more or less friction if I were to increase this angle? What would happen to the amount of friction if I were to increase the angle of inclination? I don't mean the frictional coefficient, Jay. Is that what you were thinking? Maybe. Okay, well let's think about wheelchair ramps, right? Wheelchair ramps, there's certain code, right, to build them. You'll notice that quite often if they're retrofitted onto older buildings, they have to go like up and then turn around and come back, right? Why do they do that? Why not just straight up the stairs? Exactly, and because of friction, right? A, they're not that strong, and B, it's also a safety thing because of the friction, right? The lower the ramp, the greater the amount of friction. Even if you imagine if you've got someone walking up that ramp, right? You still have to have it a certain incline, right? For safety reasons. So, in fact, as you increase the ramp, the friction force decreases, which in some cases is good, in some cases is bad. Okay, so the quantities Fn and Fd are simply the components of the weight force. This is important. They're not new forces, they're just components of gravity. That's all they are. In different directions, right? Down the plane and perpendicular to it. If you want to call them X and Y, go right ahead. I'll pause. We're going to look at that triangle there. Okay, I'm going to pull out from the diagram, I'm going to pull out this little triangle right here. Okay, let's just do this for the time being here. Remember that this is theta. It's the angle of the ramp. This is the weight force. This is Fd, and this is Fn. Using what you know from grade 9 trigonometry, what are the sine, cos, and tan ratios? Actually, what are the... Give me what the sine ratio is. You think I'm wrong? When do you do trigonometry now? Oh. Well, that's all I'm wrong about today. That's a good day. Grade 10 is trigonometry? Okay. Well, regardless, what is the sine relationship for that triangle? FD, sine is opposite, FD over FW. Now, because FW is equal to mass times gravity, could we say FD over mg? Or in other words, rearrange that to FD is equal to mg sine theta. The force down the plane is mg sine theta. Theta, of course, being in degrees. None of that silly radian stuff for us. What is the cosine relationship? Adjacent over hypotenuse. Adjacent is Fn over hypotenuse, Fw, which we've already declared to be mg, and you get Fn is equal to mg cos theta. We just derived a couple of new formulas. It was a whole lot simpler than those other ones that I did that one time. Remember that fun day when we derived 3 new formulas? Fractions and such?
And when I realized that we wouldn't actually have to use that.
Yeah, and there was that big sigh of relief.
Yeah.
Okay, so that's all you really need is those 2 formulas. Those are the ones that give you, for now, for today only, because we're going to be talking about frictionless planes. That's the important one. When we get into inclined planes that have friction, we're going to deal with this one. How come? Because remember, mu is equal to FF over Fn. Right? But not for today. Let's do a sample one, shall we? I'll give you a moment there to jot it down. All right, so I have here a 30-degree angle. I have a 1 meter long ramp for all intents and purposes and a 5 kilogram object. And then we're going to be asked to find various things. More or less as you progress, getting more and more challenging, I'm not going to ask you to find those things. You're just going to have to notify. But for today, I'm going to ask you to find them, right? So you can see how to get them. Whoa. I guess I'm, okay. I'll have to, I guess I'm missing some slides. Okay, that's fine. No problem. What's the first thing I got to find? FW, right? FW is easy. It's equal to mg. Should you always find the weight force? Pretty much, right? Unless it's given, there might even be a mark for it. It's pretty much always, you're going to need it, right? So in this case here, it's 5 times 9.8 or 49 newtons. Great question, Jake. Usually that question comes a little bit later, but let's deal with it now. Jake wants to make gravity here negative. What do you think? Who wants to join Jake on his petition to make gravity negative?
I want to make gravity negative.
Yeah?
I could just ask him to have.
No, he's an activist.
Okay.
It's okay to do that, but because now we're dealing with 2 dimensions, right? Like traditionally, negative, positive, negative, right? But generally, they never really coexist, with the exception maybe in a vector situation, right? But the problem here is that now we've taken everything, we've taken that, actually I should redraw that. We've taken that whole thing and done what? We've taken this entire thing and done that, right? And so now, not only do we have down being negative and up being positive, and okay, now what? Is it like that way, or now do we have these? We're almost talking 3 dimensions here, right?
Okay.
So while it's not terrible, Jake, it might be more work than it's really needed. What I kind of prefer to do is there any motion in that direction? Is there any motion straight down? No, right? So we really don't need to assign that direction a positive or negative sign, right? We can define that. In fact, what some books will do is they'll define down the ramp as negative and up the ramp as positive, right? So really, to make the answer short, No, you don't. Right? Because we're really only interested in numerical values so far. When we start dealing with directions, then we're going to have to start worrying about that. Does that make sense? Maybe that's not the worst spot to deal with it instead of later. Okay, so the weight force is 49. I guess there might be some professors that would insist on you putting like absolute value. That actually means like the numerical value of the vector, so just the 49 instead of, but that seems a little bit extreme. We won't worry about that. No, I'm not going to worry about that. Okay, D. F perpendicular or F normal is mg cos theta, or 5 times 9.8 times the cosine of 30, or 42.4, I believe. Yeah. Mg cos theta? The question is that theta, is Fn always going to be mg cos theta? It always depends on the angle. If the angle is ever moved, then that changes the cosine sine relationship, doesn't it? Right? Like if the angle was the other one in the triangle, then it changes, right? Is the angle ever going to be different? Like, am I ever going to describe an angle of a ramp with that angle in there, which I'll call beta, just to have it different? Is it ever going to be described as that? I mean, I guess it could, but not very likely, right? And if it was that one, then it would actually be this one here, wouldn't it, right? So the short answer is no. Or I mean, yes, it will always be the mg cos. It's never going to change, right? Only because that angle is never going to be. Okay, good question. So Fn is mg cos theta, and I'm pretty sure the next one's going to be Fd, right? Mg sine theta. And likewise, Brandy, that's always going to be the sine. $24.5. Okay, so those are sort of the base things that we need to know. To find the net force, let's just write here, Fd is the force accelerating the object down the plane. Are there any other forces? I'll just draw it here so I don't have to flip back. Are there any other forces on this object? I mean, one is pulling it against the plane. There is a normal force doing that as well, right? But is there anything else? Certainly not in this plane in that direction, right? The net force is equal to Fd, is it not? There's no friction. There's nothing else in this direction here. Right.
But if there was friction, we'd have to.
Oh yeah.
Okay.
Which way would friction be? It'd be like that, right? And then the net force would be Fd plus Ff, with Ff being negative, and that's where we got to start introducing the negative signs, right? Okay, so what does that mean? Well, that simply means, oh geez, skipped ahead here. That simply means that F net is equal to Fd, and F net then is that number that we just came up with, which was 24.5, right? So F net is equal to ma. 24.5 is equal to the mass times the acceleration, and the acceleration of the object down the plane is 4.9 meters per second. Right? I went a little fast there and a little messy. The net force is the Fd. The F net is 24.5. F net equals ma. Solve for Fd. What's the direction of that 4.9? Because it's supposed to be a vector. I mean, the direction technically is down the plane, right? And the textbook professors would probably insist on that being in there. I'm a little more easygoing. I think we all know the acceleration down the plane. I'm taking way longer at this than I'm explaining, right? It's not going to be near this complicated. Time to get to the bottom. This is part D here. Time to get to the bottom. How long is it going to take for it to slide down the ramp? I need something with T in it. What else do I know? I know acceleration. Yeah, we've gone past the bridge, right? We're into kinematics now. Initial velocity, 0. Acceleration, 4.9 p squared. T is going to be the inverse square root of 2 times 1 divided by 4.9, or I get 0.64 seconds. Say again? Seconds. Anything new here at the end? Like, this is just old stuff, right? We're just adding on another layer. And same thing in part F. VF equals VI plus AT, I think, right? How fast is it going when it gets to the bottom? 4.9, my T is 0.64. .14 meters per second is how fast it's going at the bottom. This is all true because there's no friction. I'll pause for a second. This is the last part here. Note that on a frictionless surface, F net is equal to Fd. I'm going to do a little bit of formula manipulation here. Let me pull my shade up there. What does this mean? If the F net is equal to Fd on a frictionless surface, put F net, put the value of F net on one side of the equal sign, like the formula, Ma, and put the value for Fd on the other side. And you should see Ma is equal to mg sine theta. Right? And then what is your magic math spidey sense telling you? Units cancel?
Or
You're right, something's canceling. Quantities, mass. The mass cancels, doesn't it? No, that's a quantity, right? So in other words, on a frictionless ramp, the acceleration is equal to g sine theta. Only true on a frictionless ramp. What does that tell you about the mass of objects that are sliding down hills? Contrary to what most people believe, the mass really doesn't matter.
is that a frictionless?
Well, it shouldn't be. It sort of depends on how much friction there is, right? Now, experience tells us, like when you go to Mississippi and you got a 250 pounder on a inner tube compared to a 50-pound child, which one's going down the hill faster? The big guy, right? But why is that? And I don't really know it. Absolutely, yeah. Just go ahead. So you have a little worksheet there. I think there's 4 questions. Am I right here?
Yeah.
4. Okay. I would say those ones are probably a little more on the easier side. I would suggest to start with those. They're a little bit more sort of the ones where I say do this, do this, do this, do this, and that's it, right? Like, wasn't charged, don't think, just practice kind of thing. The ones in the book there are a little bit more challenging. They will involve a little more challenging situations. I know there's one where there's like a cow on roller skates going down a icy hill or something like that. I don't quite remember how it works, but it's a little bit more challenging. So, yeah. So again, start with this sheet, try those later, you got lots of time. I'll make a decision about whether we're going to go on tomorrow or whether you guys need more time at the end of the series.